This is the first part for lesson 11.3, congruent triangles and proofs. Okay, just as a warm-up, just reviewing some ideas from the last lesson. If you haven't already done this warm-up, please pause and do so, and then come back and just check. Okay, for number 1, we had one like this. You're going to tell which congruence test. Remember, you have side, 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 angle, or angle, side, angle to choose from. And so we did have one like this earlier. We've got these side, this side, and then this is congruent to itself. So this is going to be side, side, side. It does say to write a congruent statement. So I'm going to say triangle, and I'll say DAT is congruent to triangle DET. If I held to my writing it in alphabetical order, I'd be doing it like that, I guess. And so I'd say EDT for that. So either one, it's fine. Just for consistency, I guess I should be putting that. Okay, number 2, we have got an angle and I've got a side, but I don't have anything else. 2 pieces is not enough here, so angle and side, that does not do it, so I do not have enough information. Okay, number 3, I've got these two sides, these 2 sides, and then I've got these vertical angles. Even if these 2 angles were not marked, so if they weren't marked at all, if I just had like the sides only, you would still be able to prove it because you would say these 2 are congruent because of vertical angles, so therefore I have side, angle, side. And so if I do my congruent statement, I'm going to say triangle ABC is congruent to triangle, and then what matches A? It's not D. Okay, A is going to go to C, and so I'm going to say ECB. So here's an example of where you see that B's don't match up. Okay, that's fine. That doesn't always happen. Okay, for number 4, this is kind of an introduction, and so if you didn't get all the way through this yourself, that's fine, but this is kind of an introduction to how we're going to set up our proofs. And so when we prove whether or not these 2 triangles are congruent, using side, angle, side, so it could be true or maybe not. And I've kind of set this up the same way where we've got the side and the angle and the side. But what a proof is it gives us every single little step here that we're going to need to do. So we have our pictures, and I noticed that I have 2 right triangles. I've got 2 of the sides, and so I can find the missing side on each one of them, and so that's something I'm going to want to do. The way I've got this set up, though, it does say given, and that's always going to be your first step of a proof, is just to list what you already know. So you'll notice that it says LN. I already know that one, so we're just going to write 45, and that's why it's given. It's given, and so I didn't have to do anything to find that out. MN is also given to me. TV is given as well. The measure of angle N is 90 degrees. That's given because of the symbol. The measure of angle V is 90 degrees because of the symbol, and then TU is 52. And all of that was given in the picture. You didn't have to calculate anything. You didn't have to use any theorems or anything like that. Now, the next thing, it says find UV. And so I'm looking for what is that. And on this side, we have what are called our statements. And then on the right side, we have what are called the reasons. And so if you look over at the reasons, I'm giving you a hint that we're going to use the Pythagorean theorem to find UV. And so if I say 45 squared plus x squared equals 52 squared, and then I do my calculation, so I'm going to have x squared is equal to, it's going to be 52 squared minus 45 squared. And so 679. Since that doesn't come out to be an exact number, you get a decimal. And so you can check and see if you can simplify that radical. 679 actually comes out to be 7 times 97, and 97 is prime. So there's actually nothing you can do to simplify that radical. So it's just going to be the square root of 679. So I'm going to put square root of 679 for that one. And so let me label the picture too. When you're doing this, you want to make sure your picture is labeled so you can use that, so you can see whatever it is you need to see. I'm going to find my hypotenuse right there. I know I'm going to need to do it most likely, so let me go ahead and find that. I'm going to say 28 squared plus 45 squared. And that's 2809, and so then when I take the square root of that, it's 53. So I can see right there I kind of have a problem, because what's happening is this leg of the right triangle is not matching this leg of the right triangle, and the hypotenuse of the right triangle is not matching the hypotenuse. So this is not going to be a situation where we can prove that they are congruent. So I'm going to say LN is congruent. That's the hypotenuse. or sorry, that's not the hypotenuse, that's this side right here. So I'm going to say ln is congruent, and it says not equal to, it says congruent, so I need another segment. And so the side that it's congruent to is the TV, and so I'm going to write TV, and that is true. And then angle N is congruent to angle V, so that's true. The problem comes in is that LN, oh, I think I have that wrong. That should be MN, sorry. MN is not congruent to UV, and so because of that, triangle LMN is not congruent to triangle TUV, and that's because side angle side is not met, so the conditions of that are not met. Okay, number 5, it says prove whether or not triangle FHG is congruent to triangle VXW using side, side, side. So I'm going to need to find all 3 sides. I'm not given anything except for the diagram, and so as far as writing out what's given, I don't really have anything. I am told that I'm going to be using Pythagorean theorem or distance formula, and so I know how to do that. And I'm being asked what all of the sides measure, so I'm going to use Pythagorean theorem to do that. So pause the video if you haven't already done this one, and go ahead and find all of the sides, and then come back when you have all 6 sides. Okay, I have all of my measurements that I found using Pythagorean theorem. What I did was on all of my just mapped out the triangle and then used the Pythagorean theorem to do that. So I've got all of those listed. The reason that I knew what they all were is because of the Pythagorean theorem. Okay, the next part of the proof that's mapped out is it says Vx is congruent to. So which side is Vx congruent to? So Vx is the same as Fh, and so I'm going to write that it's congruent to Fh. Xw is congruent to Hg, and Vw is congruent to Fg. And so that's something I found out from that first section. And the reason I know that this is congruent to this is because since they have equal measures, that's the definition of congruent. So the reason I put it is a saying that we have in geometry. It says congruent parts have equal measures. So if you have 2 parts that are congruent, that also means that their measures are equal. So as my conclusion, I'm going to say that triangle VXW is congruent to triangle FHG, and the reason is because of side, side, side. Okay, today we are going to look at the other 2 congruence tests. So remember in the last lesson we learned about the 3 congruence tests, and these are all postulates. And so we talked about those, and we also talked about what was not a congruence test. And then I mentioned that there's 2 other theorems that are congruence tests, and so today we're going to look at those. These are both theorems. The first one is called angle-side theorem, and it's called a theorem because you can actually prove it. So you can prove it using other things that we know, and we're going to maybe talk about that in secondary too, but not really right here. It says that if 2 angles and the non-included side, so that means you have an angle and the side that's not included. So if I was talking about the included side, then I'd be talking about angle, side, angle, which we already did. So this is if you have 2 angles and a side that's not included, and then 2 angles and a side that's not included, that's actually going to be enough to prove this using angle, angle, side. This is the visualization for angle, angle, side. So on my left, I've got the angle P, and then I've got angle R, and then the side RQ. And so as I change that, you'll notice that the corresponding angle and angle and side on the right will change to go along with that. If I keep my angle P and R being the same, and then the side RQ is the same, there's no other way I could create a different triangle. So if I took this side right over here and I moved it so it went like that, that's going to change the angles. So to keep the angles the same and the side being the same from triangle to triangle, there's no other way that you can do that. And if you think about when we saw why side-side angle doesn't work, you saw that the reason it doesn't work is because there's more than one possibility. There's no other possibility that you could do for this here. This side and this angle are fixed. The other angle has to be fixed. The gray parts, they can change, but the blue part, it has to stay the same from triangle to triangle. So that's the reason why it doesn't work. The next theorem is called HL theorem, and that might catch you off guard because we're used to using the A and the S. But HL, so because it's hypotenuse leg, because of the word hypotenuse, that means this is only good for a right triangle. You cannot use this theorem if you have any other type of triangle. So if you have a right triangle, then If the hypotenuse for each one is the same and one of the legs is the same, that's enough. Now you might notice that if you look at the diagram, if you have a right angle and then you have these two sides, and just to be proper, I'll write that, and you're like, well, wait, that's not true. And you're right, it's not true. That does not work unless it's a right triangle. So if it is a right triangle, that actually will work. And so because it's only for a right triangle, that's why it's called hypotenuse leg. So only if you have a right triangle can you do that. This is the visualization for hypotenuse leg congruence test. So in these triangles, you'll notice that I have a set right angle, and then the hypotenuse is going to be set and the leg is going to be set, and that just means that from one triangle to the other, they have to stay the same. So if I keep the hypotenuse and the leg the same, there's no other way that I could create a triangle that would have the same hypotenuse and leg and right angle from one triangle to another. So if you remember with side-side angle, it didn't work because there were two possibilities. Because of the right angle in this one, it fixes the possibility. So it makes it that it's impossible for you to take this leg and go on the other side with the hypotenuse and have it be a different triangle. It's going to be exactly the same because of the 90-degree angle. Okay, a proof, a mathematical proof, and we've talked a little bit about this like with the warm-up questions, but a mathematical proof is an argument that convinces other people that something is true. It has to have a definition or a theorem or property for every single statement. So every single thing you say, you have to back it up with a reason why. In math, especially in lower math, like what we're doing right here, is we start out with two-column proofs. There's other ways to do proofs, but a two-column proof is a really good way to organize something. And so you have two columns, you have a statement, and you have a reason. And so it's just a very neat evidence-based way to set up your proof. Okay, something I've mentioned earlier is the reflexive property, and the reflexive property says A is equal to A or anything is equal to itself, and we use that a lot. Or if we say like the segment AB is congruent to itself, and we saw some examples of where we would use that. In the warm-up right here, we use the fact that DT was congruent to itself, and that's the third side of that triangle then. So we had this triangle is congruent to this triangle because that third side was equal. Okay, the next property is called the substitution postulate or substitution property, and you've actually been using this for a very long time. It just says that a quantity can be substituted for its equal in any expression. So we've used this before when we solve systems of equations. You solve it every time you substitute a number in to see if an equation is true. And it just says if A is equal to B and B is equal to C, then A can be substituted in for B because it's the same thing, and then you get A is equal to C. It's just saying that one thing can be substituted in for another. Okay, the next one I mentioned back in the warm-up, and it said congruent parts have equal measures, and this reason you can use it after you've listed the measures of corresponding parts. So if you've already said that this, angle is equal to this many degrees and this angle is equal to this many degrees, then you can say that they're congruent because they have equal measures. And same thing with the sides. And so that's just some of the reasons that we use in proofs. And so these are just reasons that are pretty common to be using in a proof. Okay, the rest of this lesson will continue in the second video.